Shall we start now? Hello.
Okay, sir.
Okay. So, did you go through the slides or the recording uploaded last time regarding this unit step? No? Actually, so if you remember, so we had this discussion regarding the switches. So we basically have this kind. Can you see the screen?
Yes, sir.
Yeah. So we have this kind of a setup. So this is the one model of switch having this T. So the other model is this. So here we identify that this particular switch was basically off during t less than 0 and t greater than or equals to 0. This is basically on, and if this arrow is into this direction, so this is basically on when t less than 0 and t greater than or equals to 0. This is basically off. So this is the basic operation of these two types of switches. So you can easily identify those by looking at the direction of this arrow and this value. So this value and the direction of this arrow, direction and the value. For example, if you have this kind of a switch, so this switch, the operation of this switch actually can be defined like that. So this switch is turned to on at t equals 10 seconds. So it means t less than 10, this basically was in off state, sorry. So this is basically in off state. So greater than or 10, this is basically moves to on state. So likewise, you have to basically think of this value and the direction of this arrow. So by looking at these two quantities, you can easily decide the operation of the switch. So if you plot this operation graphically, so you can see like when t is less than 0, this switch is off, and t greater than or equals 0, this is on. Like if you just draw it, so if this is the time axis, so this is the voltage or whatever the current axis. So you can simply explain this operation like this. So here you may have whatever the value of the source, either it may be a voltage, it may be a current. So at t equals 0, the state moves to on. So during this t less than 0, this is basically off and this is basically on. Similarly, you can map this operation of this switch again like this. So this is t equals 0. So until t equals 0, this switch basically was in on state, and at t equals 0, it simply jumps to the off state. So this is the graphical representation of these switches or the operation of the switches. So we can basically replace this graphical representation using unit step. Okay. So we define our unit step function ut like this. So this ut is basically defined like this. The value of ut is 1 when t greater than or equal 0 and 0 otherwise. So if you draw it, it's something like that. This is ut. Here it's 1. This is 0. Okay. So from minus infinity to 0, the functional value is 0. Then from 0 onward, it simply jumps to a value of 1. So this is the unit step. So by looking at the definition of the unit step and the operation of this switch, we can simply say that this operation can be represented using a kind of a ut times A. If this amplitude is A, you can simply replace this operation or the switching operation using this mathematical model A times ut. So ut is actually 1. Ut is actually 1 when t greater than or equal to 0, otherwise 0. So it means like during this negative values of t or minus infinity to 0, the output of this A times ut is basically 0 for less than 0. This is A when t greater than or equal to 0. So likewise, you can replace the second operation using this switch A times u minus t. So the definition of u minus t is actually, so this is 0 and 1, t less than or equal 0, t greater than 0. So if you draw it, it's something like that. Here t equals 0, this is t, this is actually u minus t. Okay, the value of this point is plus 1. So from minus infinity to 0, the value is actually 1. And from 0 onwards, the functional value is 0. So then we can replace this operation using A times u minus t. U minus t is actually the mirror of this ut, mirror of ut. So how do you take the mirror? So you can just rotate over the y-axis. So then you can easily get the mirror of this particular function. U minus t is the mirror of this ut. So by replacing this operation with A times u minus t, so you can basically get the same output. So this is actually A t less than or equal to 0, 0, t greater than 0. So during minus infinity to 0, the functional value is A, and otherwise functional value is 0. So likewise, you can simply replace the switching operation which we discussed previously using a mathematical function. So this is called unit step. So you can simply replace the switching operation by unit step function. So then so you can simplify the network by replacing the source and the respective switch using a kind of a unit step. So then you may have some examples or some circuits having this unit step function as a source. Rather having this traditional voltage and current sources, you may have a kind of a unit step function to replace this operation or the impact of these sources. So then depending on the behavior of the unit step function, you can decide whether this source is effectively contributing to the circuit or it's a kind of a isolated model. So I actually discuss one example which is actually in the slide set. So how this voltage source can be replaced using a unit step, and if you have this unit step function or a kind of a combination of unit step functions as a source, how do you manage to get the responses by looking at the behavior of the unit step? For example, so I can give a small example. So think of this function ut minus ut minus 2. Okay, so this is your source. So this is the source. So how do you get this impact of sources? You have to draw the entire function. So ut minus 2. So this is your ut, t equals 0. So the functional value is plus 1. From t equals 0 onwards, the functional value is 1. Otherwise, it's 0. This is ut. So then we'll draw the ut minus 2. Ut minus 2 is actually, so this is actually ut is basically shifted by 2 units to right hand side. So it means if you plot this, so this is t equals 2. So this ut is simply shifted by 2 units to the right hand side. So this is ut minus 2. So the 0, the value at t equals 0 is basically push it to t equals 2. So this value actually moves to this point. So then you can easily get the ut minus 2, which is a shifted version of this original function ut. So if you simply subtract ut minus 2 from ut, you basically ended up this kind of a pulse. During the 0 to 2 region, 1 minus 0, you have 1 here. From t equals 2 onwards, you have 1 minus 1, which is 0. So then ultimately we'll end up with this kind of a switching operation. Here 0, here 2, the value is 1. So then you can replace the switch like this. At t equals 0, you have this kind of operation. At t equals 2, you have this kind of operation. So then each and every edge of this can be replaced using this unit switches. So by considering the other way, any kind of a switching operation can be replaced with unit step or kind of a combination of unit step. So then rather having the sources in the circuit, you may ended up with scenarios where you can replace this existing voltage or current source with this unit step function or combination of unit step functions. Okay, for example, if you take another one, so this is your voltage source GT, which is equals to 2 ut minus 1. So if you elaborate this, so we have basically t less than 0. So you know that ut is actually defined from t equals 0 onwards. So this is basically defined from t equals 1 onward. So this is like this, t equals 1. This is like this, t equals 0. So then t equals less than 0. Basically, the value of gt is 0. So during the 0 and 1 interval, so you have 2 here, here 0. So then we have a functional value of 2 between 0 and 1. So from 1 and onwards, so we have 2 from unit 2 ut and 1 from ut. So 2 minus 1, actually 1, t greater than 1. So we have 3 states. If you graphically show it, 0, so then jumps to 2, then jump back to 1, like this. So this is t equals 0, jumps to 2, so then jump back to 1 at t equals 1. So likewise, any kind of a staircase scenario or kind of a pulse, rectangular pulse, can be replaced with unit step. And at the same time, any kind of a switching operation can, or along with the source, you can simply replace the source and the switch using a unit step function. So this is the simple summary of the last session. So do you have any questions so far? Okay. Next, we'll move to the next section. What happens if we have sinusoidal sources? Sinusoidal sources. It means like rather having this kind of a constant fixed DC source, your voltage would be this. Vm sin omega t kind of. So it's a kind of alternating signal. So until now we consider a scenario where we have sources, but those sources are DC sources. So then we came with this kind of a differential equation. So dxt over dt plus kind of a naught xt equals kind of a constant. So these two cases we already discussed. A naught xt equals 0. So equals 0 means, so we claim that for this particular case, we don't have sources. So this is without sources. So if you ended up with a kind of a first order differential equation having this right hand side, a kind of a constant, so then we claim that so this particular circuit contains external sources, but those sources are DC sources. So that's why we'll ended up with a kind of a constant the right hand side of the differential equation. So if you have fixed DC sources in the circuit which are actually powered the circuit, so then your differential equation or the system model can be like this. So you will ended up with the first order differential equation if it is a first order circuit, but at the same time right hand side would be a kind of a constant. It may not be exactly the value of the source, but a kind of a constant which can be basically derived from the value of the sources. So we had went through couple of equations. Okay, so the third scenario is, so for this case, for this model, we found that whatever the sources we plug into the circuits are DC sources. So then what happens if you plug a source like this? If you plug a source like this, it's a kind of a AC source. So what happens actually? So you will ended up with a kind of a sine or so right hand side would be a kind of a function of sine omega t or kind of a cos omega t. So it depends on the scenario. For example, like your source is just scaled by kind of a resistor or a capacitor. So then your right hand side would be a sine function. So sometimes there may be scenarios you have to differentiate the entire expression. So then the sine omega t would be converted into a cos function. Is the once you take the derivative with respect to t for this entire expression, then your right hand side, the source value is sine, but once you differentiate it, it simply converted to cos function. So basically your right hand side would be ended up with either a kind of a sine function with the same frequency or kind of a cosine function with the same frequency with different amplitude. So we cannot guarantee that the amplitude is exactly Vm. It may be either scale up or down depending on the coefficients appear here in the left hand side. But we can simply say that definitely the right hand side would be a kind of a sine function or cosine function. Okay. So then what would be the forced response or the trial solution for the forced response? For this kind of a case, forced response would be kind of this format: a cos omega t plus b sine omega t. So this is the trial solution for this sinusoidal sources. Because if you have a sinusoidal source in the circuit, you will definitely will be ended up with a kind of a sine or cosine term in your right hand side of the differential equation. So it means your force term, so the force term ideally would be either cos function or a sine function, either cos or sine. So then we know that if we want to find the trial solution for this kind of a scenario, so the trial solution for the forced response would be ideally synchronizing with the pattern of this right hand side or the force term. So if it is a constant, we can propose a kind of a forced response which is again a constant. If it is a sinusoidal or cosine function, we can propose this as the trial solution. So the forced response, the trial solution would be a kind of unknown constant cos of this omega t plus b sine omega t. I think you got the point. Any questions? No? Okay, we'll take one example. So it is in this circuit. So we have inductor, resistor, a capacitor. So this is 2 Henry, 2 ohm, 1/10 farad. We have source. So this is like 15 cos 2t. Yes. So this is the voltage source, and the value of the source is 15 cos 2t. So we have a circuit having both inductor and a capacitor. Okay. So how do you get this expressions? So if you apply Kirchhoff voltage law, so if you apply Kirchhoff voltage law, so the voltage drop across this 2 ohm resistor is like 2 times current IT plus, so the drop across this inductor would be L times IT dt. So this L is actually 2 Henry. So then the voltage across the capacitor is actually, if you replace the voltage across the capacitor as a function of current, it would be like this: 1/C integral I tau d tau plus V0. So this is the voltage across the capacitor in the form of current, which is equals to 15 cos 2t. Okay, so this is equals to 15 cos 2t. So then if you want to get the differential equation, so we have this integral term. So how do you remove the integral term? So you can basically differentiate the entire expression. So if you differentiate the entire expression with respect to t, so then we have 2 times derivative of this current plus L equals 2. So this derivative, again on top of this derivative, it would be 2 times the d squared it or dt squared. So then we have an integral term. So then we have 1/C. So then it's become 10. This integral can be replaced like this it. So if you differentiate this integral, you can just replace this integral with this it. So then V0 is the kind of a constant, which is actually the initial condition of the circuit. So it's a kind of a constant value. So once you differentiate with respect to t, so it would be 0. So then the right hand side would be 15 cos 2t should be differentiate with respect to t. So then 15 is there. Cos 2t becomes sine, and then this 2t, so we have again So we have minus 15 sine 2t times, so altogether minus 30 sine 2t. So if you simply divide this by 2, so then we'll end up with d squared it dt squared plus dit over dt plus 5 it equals minus 15 sine 2t. So hope it's clear. So now this is the differential equation. So unfortunately, it's a kind of a second order differential equation. And the right hand side of the second order differential equation is actually a kind of a sinusoidal function. Now this force term is a kind of a sinusoidal function. So then if you want to find the force response, so how do you get it? So you can come up with a trial force response IFT, which is equals to, or which is aligned with the pattern of this right hand side. So if it is a sinusoidal or the trigonometric format, so we should basically come up with a kind of a general form, so which is equals to a cos omega t. Now this omega t would be 2t plus b sine 2t. So this is your force response or the trial force response. So if you have a kind of a sinusoidal or a kind of a trigonometric type of function in your right hand side of the differential equation, the trial solution for this force response would be a cos plus b sine. So then if you want, so how do you find the unknown quantities is basically, so you can replace the force response, or assuming that it's a kind of a solution for this original differential equation, and substitute that response to the differential equation and find the unknown constants. So what we can simply do here is we can replace this it terms there in the differential equation, assuming that it's a kind of a solution of this differential equation, and if it is a solution, it should be satisfy the original differential equation. So you can substitute this a cos 2t plus b sine 2t to this differential equation and find a and b. It's like this. So d squared over dt squared a cos 2t plus b sine 2t. Then you have a derivative here, first order derivative, a cos 2t plus b sine 2t. Then 5 times it a cos 2t plus b sine 2t. It should equals to 15 sine 2t. So then you can simplify the, or you can evaluate the second order derivative and first order derivatives. So you can find the values for this. So then you can simply equate the coefficients in the right hand side and left hand side by considering the sine and cosine terms. So you can basically find the A and B from this. A and B. Okay. So as a summary, if you have a source, sinusoidal type of a source in your circuit, so then the force term or the right hand side of the differential equation would be a kind of a sine or cosine function. So in that scenario, you can basically replace or suggest the trial solution for the force response, in this format. This is the more generic form you can use for any kind of a sinusoidal signal, because if your A value is 0, then we can simply say that the output would be simply aligned with sine function. If your B is 0, you can simply say that your output would be aligned with the cosine function. If those constants are basically non-zero, your output would be a mix of sine and cosines. So depending on the values you can get it for the A and B, you can simply claim what would be the output actually. So hope it's clear. Any questions? No? Okay, shall we try one example? So we have a source, inductor, okay. So you are asked to find the current flow through the circuit or the current response of the circuit. So this is a kind of a voltage source. And if you apply Kirchhoff voltage law, voltage drop across the inductor would be L times the derivative of the current, L dit over dt plus 4 into it, the current voltage drop across the 4 ohm resistor, which is basically equals to 6 cos 2t. So the L is basically 1 Henry. So then ideally you will ended up with this kind of a first order differential equation. So this is your first order differential equation. So then how do you find the force response? So the first term would be 6 cos 2t. So then you can propose a kind of a trial solution for this first response as a kind of a cos 2t plus b sine 2t. So depending on a and b, you can find the exact response. How do you find the a and b? Find a and b. So you can just, so this is a trial solution. So definitely this differential equation should be satisfied. So you can substitute this I to the original differential equation. So then it becomes the derivative of a cos 2t plus b sine 2t plus 4 times a cos 2t plus b sine 2t should equals to 6 cos 2t. So a cos 2t, if you differentiate it with respect to t, so this becomes 2a sine 2t. Here minus, here 2b cos 2t. Here you have 4a cos 2t. Here we have 4b sine 2t. 6 cos 2t. So then you can basically equate these coefficients of cosine and sine. So here for cos 2t, if you equate the coefficients on right hand side with left hand side, so we can cos 2t have 2b here plus 4a equals 6. So then if you equate the sine 2t, so we have minus 2a plus 4b equals 0. So then you will ended up with these two linear equation to solve this a and b. So then you can simply find this a and b. So as the value of a and b. If you just multiply the second one, 4. So then 6b is equals to 6, b equals 1. So then b equals 1 means a equals 2. So then your first response, IFT, would be 2 cos 2t plus sine 2t. Okay. So this is your first response. Yes. Yeah, sorry. So this should be like 605, 305. Yeah. So this is not 6, this is 8 actually. Sorry. So then this is sorry, not 8, 10. So then this is 305. This yeah. So this is 605 cos 2t plus 305 sine 2t. So this is the ideal force response for this particular circuit. So hope it's clear. Like if you have a kind of a sinusoidal source in your circuit, so which would be the external source you plug into the circuit to power the circuit up. So then you will basically ended up your force term or the right hand side of your differential equation again in the form of cosine or sine. Depends on the rest of the coefficients in the circuit. So anyway, it should be either cos term or a sine term. So then we can replace the, if you are asked to evaluate the force response, we know that the force response should be aligned with the force term. So then according to the force term, we can propose a trial solution. So if it is a cosine or sine function, so we can generally replace the force term like this. Having both cosine and sine, so then depends on the A and B, we can decide whether it's a completely aligned with the sinusoid sine function or whether it's completely aligned with the cosine function or sine, depending on the values of A and B. So then you can find these values A and B by just substituting this force response to the original differential equation. So because the whole idea is whatever the proposed trial solution would be ideal solution of this differential equation. So if it is a solution of the differential equation, once you substitute the force response to the original differential equation, it should be satisfied. So based on that, we can simply substitute the force response and find the unknown coefficients A and B. So once you find this A and B, we can easily find the ultimate force response of the circuit. So hope it's clear. If you want, you can further simplify this one. So you can further simplify this. Because so we have cos function and sine function. So you can basically represent this as a kind of a cos A, cos B plus sine A, sine B format. Isn't it? So this so cos A minus B would be cos A cos B plus sine A sine B. So this pattern is very similar to this cos A cos B plus sine A sine B. So then you can find this A and B So these values, and we can simplify this forced response to the same format. Yes, so for example, so then this can be simplified to a kind of a constant, let's assume k cos 2t minus 4 plus theta. So this can be basically simplifies to this form. K kind of a constant depending on the 605 and 305, and this cosine 2t plus or minus theta again depends on these values. So these theta can be easily defined as a tan inverse term, and depending on the value you can get it for the tan inverse term. You can simplify, think of like it's a plus theta or minus theta, and then you will end up with a kind of a known constant in front of this cosine term. See that? So you have a kind of a cos 2t type of a source, but due to this inductance, basically due to this inductance, your response would be this cos 2t plus or minus theta. See, you basically apply kind of a source in the form of cos 2t. So due to this inductor, or if you have capacitor also, you can observe similar impact. So due to this inductance, your response is basically added with this external phase shift. So due to this energy storing element, either maybe a capacitor or inductor, or with the both elements, your response would have a kind of a phase shift. So this phase shift is basically due to this inductor or a capacitor, if you say. So then if you apply kind of a sinusoidal type of a source to the circuit, your force response or the contribution of this source is simply affected by the connected inductors or capacitors in the circuit as a kind of a additional phase shift form. So you will end up with a kind of an additional phase shift to the response. So this additional phase shift is simply based or depends on this one. So then you can come to a conclusion. It means like your response, force response. So last time we argued that force response is the steady state response of the circuit. Force response is the steady state response of the circuit. So the steady state response can be manipulated by inductor or a capacitor or a combination of inductor and capacitor by introducing kind of a phase shift. So it means you want to adjust your waveform by shifting it to the left hand side or right hand side through this external energy storing device, which is a kind of inductor or capacitor. So by introducing inductor or capacitor, you can basically shift your output by adding a certain phase shift. So this is the conclusion we can made out of this kind of a circuit. So this is the analysis part for this particular circuit if you have sinusoidal type of sources in the circuit. Is it clear, or do you have any questions so far? No? Okay, so just for another sake of clarity. So we should, so hope you have idea about this Euler's transform. So if you have this kind of a complex exponential, so you can convert it into this form, cos theta plus j sine theta. Okay, so this is the real part of the complex number, and this is the imaginary part of the complex number. Okay, so this is the angle of the complex number, and this is the amplitude of the complex number. Okay, so if you want to write this complex number in the polar form, so it's something like that, 1 theta. So theta is basically appear here, 1 is the amplitude. So theta is appear here, here, and the amplitude is basically here and here. Okay, so any kind of a complex number can be represent using this kind of a polar mode or this kind of a polar mode. So this is a kind of a complex form. So if you have any kind of a complex number, you can represent it in a polar form. Polar form means r theta manner. So yeah, r is the distance vector and theta is the angle. So this can be represented using a complex exponential. It's like this, r e to the power j theta. So any complex number which is in r e to the power j theta form can be converted into r cos theta plus j times r sine theta. So this is the Cartesian or the rectangular form of this complex number. So this is your real part. So this is your imaginary part. Okay. So it's clear. So then any kind of a complex number having in this form can be represented using this r e to the power j theta. So the r would be actually, so the square root of this real squared plus imaginary squared, and theta would be actually tan inverse, so b divided by a. Okay, so it means like any kind of a complex signal can be transformed into its complex exponential. So this is the any kind of complex signal which is in Cartesian form or rectangular format a plus jb mode can be converted into its exponential format r e to the power j theta. So then r would be basically square root of the squared sum of this real and imaginary component, and theta would be tan inverse imaginary component divided by real component. So if you basically convert it into this polar form, you can represent it using this. So this is called phasor form. R theta. So if you convert any kind of a complex number into this phasor form, So it should be basically in the form of like this, r theta. So r represent the magnitude or the amplitude of the number, and theta basically represent the phase. Okay. What about so let's assume you have this kind of a signal. We know that any kind of a complex exponential can be represented using this. So this is actually, so by looking at this combination, so we can simply say that this is the real component of 15 e to the power j 2t. So if you convert this j to t, this would be cos 2t plus j 15 sine 2t. Okay. So then this 15 cos 2t is actually real component of this complex number 15 e to the power j 2t. Okay. So this is a one way of mapping this sinusoidal excitations to a kind of a complex exponential. Okay, so we'll use this theory component to simplify this sources next time. So we'll stop it for today. If you have any questions, you can raise now. So if you don't have any questions, so we can discuss it next time. So next time we basically start with second order circuits. Yes. Yeah, maybe these days the Sims is not working properly. Yesterday also I felt some loading issues. So actually I uploaded all these videos to the Sims. So sometimes once this system gets stable, you can download it. Otherwise, I can share the link with your batch representative. So then you can go through those links. So it's a kind of a public YouTube video. So if it is fine, so I can drop the link with Dilanka. So he can share it with your WhatsApp group. So until this Sims issue is resolved. Yeah, okay for today. So we'll stop it for the today, and next time we basically start with second order differential equations or second order circuits. Then for analog, we basically start this sinusoidals. Okay.
Thank you.
Okay, thank you very much.